Hey guys, I'm Patrick Pitts here with the Academic Success Center. I am a math tutor, and today we're going to talk about Calculus 2. Boy, howdy. Specifically, we're going to talk about finding the area under a curve. This is University Math Center. Let's get started. Suppose we have some function, or rather, suppose we have some curve. There are many instances in the real world, whether or not we're solving a chemistry problem, a physics problem, an economics problem, a statistics problem, where we're motivated to find the area under the curve. We have this curve defined by f of x. And I want to know in these boundaries, let's say x equals a to x equals b. I'm going to draw a straight line or else I will go crazy. And I'm motivated to know the area under this curve. How do I do that? How do I find this area? Well, the unfortunate answer is that's hard. We can use some of the same logic we used when we talked about derivatives to think about how we can figure out a sneaky way to find the area. If you recall from Calculus 1, what we did was we started by making a really horrible approximation. And using that approximation, we refined the problem. We refined the methods that we used. We refined our approximation. We manipulated it in such a way that we were able to make the approximation better. That's going to be our goal here. So how can we find the area badly? What is a bad approximation of the area under the curve? Well, one way we can do that is to say, it's kind of sort of a rectangle. I mean, it's a bad rectangle. Let's say this rectangle here. Let's say this, I'm going to claim is the area under my curve. It's bad. It's a bad approximation. I know I have all this extra area up here, but yeah, we're guessing. It's fine. So what's the area of this rectangle? Well, I need a length and a width. This area is going to be bound by this lower and upper x value. That width is going to be just b minus a. And the height is given by this y value here. Well, that's just f evaluated at a. So the area of my rectangle is, let's say, b minus a times f of a. Great, we did it. We're done, right? No. Clearly, this is not good. Clearly, this is a very bad approximation. We have this extensive amount of area above the curve, and we're not catching that. It's like a falcon outside my window. Or a pigeon. Anyway. So this area under the curve is a pretty bad approximation. How can we make it better? Well, instead of using one really horrible rectangle, maybe we could try two. So we're going to try two rectangles instead. So I'll make a midline right here, and I'll make two rectangles. There's one rectangle right there, and there's a second rectangle right here. Boy, howdy. How big are these rectangles? Well, since I cut this in half, the width of each of these rectangles is going to be b minus a over 2. The height of this first rectangle is pretty straightforward, still just f of a. But the second rectangle is going to get a little weird. This x position here is going to be x equals a plus b minus a over 2. Algebraically correct, if kind of a pain in my butt. So it's f of a plus b minus a over 2. And so our area now is going to be these two rectangles added together. B minus a over 2 times f of a plus b minus a over 2 times f of a plus b minus a over 2. Easy so far. As we can start to see, things are going to get a little out of hand. You might be able to guess where our next step is going to be. We tried 2 rectangles and we still have a bit of an error. So trying maybe 3 rectangles might be better. But using my mystical magical powers of clairvoyance, I can already tell this is going to get pretty gnarly. Writing up this formula is going to become very, very, very complicated. And not because the ideas are complicated necessarily, although a little complicated, a little complicated, but because the terms that we're going to write down are just going to get bigger and bigger and bigger. So we might be motivated to condense some things. Let's try condensing some things. So when we try to cut this up into 3 pieces, my rectangles are going to have some pretty funky values. I am motivated to define a new value. I'm going to say that funky triangle, it's a triangle, that's Greek letter delta. If you're not familiar with it, delta is used to mean change. So our change in x, when we go from one position to my next position on the graph, when I think about defining my rectangle size, I want to use delta x, my change in x. I'm going to define delta x to be equal to the width of the entire area of interest, b minus a, and divide that by the number of rectangles, 1, 2, 3. In this particular case, that's going to be b minus a over 3. But as we continue down this process, we're going to have 4, and then 5, and then 10, and then 1,000, and 400 quadrillion triangles, spoiler alert. And so rather than defining it by a particular number, I'm going to say that my delta x is actually b minus a over n. Well, n is the number of rectangles I have. Now, this is going to show up and be useful in some other ways down the line, so keep that n in mind. Now that we have this funky new value here, delta x, it becomes easier to think about the size of my new rectangles. This width is just delta x. This width is delta x. This width, you guessed it, folks, is delta x. Now, we still have a little bit of complexity in thinking about what are the actual x values. This is a plus delta x. Start at a, go forward delta x, I land at a plus delta x. Over here, next point over, that's going to be x equals a plus 2 delta x. Easy. It really is a little bit easier. Now, instead of having all of these extra variable terms that we saw in our 2 rectangle sum, it condenses down a little bit easier into this other term. So now this height is f of a. This height is f of a plus delta x. And this height here becomes f of a plus 2 delta x. So our area then becomes delta x times f of a plus delta x times f of a plus delta x plus delta x times f of a plus 2 delta x. Shocking. Now, again, we could repeat this process forever. Okay, we can do 4 rectangles, we can do 10, we can do 1 billion. We can do this process forever. But there's a couple of patterns that we can notice in here that can make doing that big giant sum easier to work with. Notice how every single term is delta x times f of stuff. Well, we could factor that out. So this is delta x times f of a plus f of a plus delta x plus f of a plus 2 delta x. Okay, great. Notice also that we have a pretty consistent little pattern in how the functions are evaluated. We start at a, and we do a plus del x. Then we do a plus 2 delta x. And if we were to have more and more rectangles, we'd do plus 3, plus 4, plus 5 delta x's. If you're familiar with the summation notation, we can condense this even further, because I want to go and I'll make a quick change here so you can really see my point. That's 1 delta x plus 0 delta x. We're adding up delta x's in terms of the positive integers, whole numbers. We do 0 delta x's, then 1 delta x, and 2 delta x, and 3. Notice also that the upper bound of that, the last number that we add, then the last factor of delta x's that we include is just the number of terms minus 1. If I start with 3 terms, that last number is going to be 2. If I was going to do 7 terms, that last number would be 6, and so on and so on. With all of that in mind, we can come up with an even more concise summation notation. I can say that the area under the curve is equal to the sum of all values where I choose some number I, it starts at 0, and I will go from all whole numbers, 0, 1, 2, 3, up until n minus 1. And I will add the following terms for every single I. That's going to be the function f evaluated at a plus delta x times I. When I equals 0, that's just going to be f of a. When I is 1, that's going to be f of a plus delta x. When f is 2, we're going to have f of a plus 2 delta x, and so on and so on. Then we take that function that we evaluated and got some number and multiply that by delta x. This formula gives us the approximation for the area under the curve for an arbitrary n number of rectangles. So we define n. We choose an n value. N is 3, n is 10, n is 1,000. Whichever n you choose, you slot this number into this function, and you eventually end up with some area.